Recording started.
All right, hi Chem30 students. We're going to do this recording here that will help you to prepare for the midterm exam. So this recording, together with the one that we did for the first test, should help you to prepare for it. I would go over the first recording again in the study guide as well. Also, I'll probably do this recording at 2 sittings because I think there's going to be quite a bit of material, so probably my voice won't hold out that long. So anyways, we'll just get started here with a little chem joke. Actually, first I will get my pointer here. Okay, so it's got a picture of a cat here. It says, tries to think of chemistry pun, best ones are gone. And if this part here doesn't ring a bell, just a reminder, AR is atomic number 18. That will help out with that one. So let's get into the chemistry then. Before we dive into a review of electrochemistry and oxidation and reduction reactions, let's review a few important concepts that are good to know for the midterm. So when we're talking about efficiency, remember efficiency, that's always percent efficiency is output energy divided by input energy times 100. And now it's always important to use, or rather I should say it's always valuable to use the input energy directly if possible, rather than converting it into another form of energy. And the reason is that there's always some heat wasted whenever you change one form of energy into another. So for example, if you have some electrical energy, if that's your input energy, if you're able to use that directly, that's always more efficient than using that electrical energy to, say, heat up an element on the stove, because then you're changing that electrical energy into another form, which is heat energy. So that's the first thing we're going to look at. Second thing is reaction rates. Now, those are the difference in concentration divided by time. If you think about what the word rate means, remember it's similar to the word speed. And so speed, of course, is distance over time, or another way of calculating it is final speed minus initial speed divided by time. Let's kind of see how that relates to concentration rates, or rather reaction rates, I should say. Reaction rates are final concentration minus the initial concentration you started with divided by time. And this right here is another way of saying the change in concentration divided by the change in time. Okay, now we're going to get right into the oxidation reduction reactions stuff. We've got a cool picture here of a combustion reaction. And what that's a reminder of is that in the beginning, when they first started talking about the word oxidation, they associated it with oxygen. So a combustion reaction is a type of reaction that involves oxygen, and so is a corrosion reaction. So again, there's just a connection between the word oxygen and the initial meaning of the word oxidation. Over time, it came to mean something different. We'll also see in this section that the word reduction, or the term reduction, is important because oxidation and reduction reactions go together. So oxidation reactions involve a loss of electrons. And so when magnesium is burned in oxygen, or when it rusts in oxygen, magnesium oxide is produced. Okay, now this reaction here is known as the ionic equation. Why is it called an ionic equation? Because you can see that the ions are shown here. So we have both atoms and ions here. Now you can see that magnesium is being oxidized. We said that oxidation is a loss of electrons. Okay, so you can see it's being oxidized. We can see the electrons are lost because we're going from a neutral charge, or a zero charge, to a +2 charge. So since electrons have a negative charge, there's a loss of charge. So oxidation is taking place. Now when we look at reduction reactions, those involve a gain of electrons. So if one atom loses electrons in oxidation, then another atom must gain electrons. So again, that's reduction. So if you look at our equation here, you can see that oxygen is being reduced. Okay, because we're going from a zero charge to a -2 charge, so we must be gaining electrons, which again have a negative charge. Now, it's always good when you're talking about biology, chemistry, whatever, to have these little mnemonics, these little words that help us remember different kind of phrases. So the one here is LEO. It stands for lose electrons with oxidation. GR stands for gain electrons with reduction. Okay, and you can look at these bold parts of the first part of the word. They help us to remember it as well. Leo and GR. And if you just remember Leo, the lion says GR. Okay. So moving along, let's just kind of test our knowledge of what we've just been talking about. So it says atoms blank electrons during reduction, and they lose electrons during blank. So atoms gain electrons during reduction, and they lose electrons during the process of oxidation. Now here's kind of a diagram that sums a lot of these ideas up. We'll talk later on about what reducing agents and oxidizing agents are. But here you can see that in one reaction, the same reaction, we've got oxidation occurring where electrons are lost. And when those electrons are lost, they're gained by somebody else. And that's reduction. So we call those redox reactions, and so a redox reaction is just another word, another name for a reduction-oxidation reaction. Okay, so we saw earlier that in a redox reaction, one substance is being reduced, and so electrons are gained. The other substance is being oxidized, electrons are lost. So in other words, what's happening in the same reaction, electrons are lost by one atom or ion, and they're gained by another atom or ion. Now we kind of looked already at one type of reaction, which was an ionic, or I should say equation. There's three different ways of representing equations. There's an overall equation, an ionic equation, and a net ionic equation. So we'll look at each one of those. Okay, so this is the overall equation. It shows the overall reactants and the overall products. Okay, and we don't have any ions involved here. In the ionic equation, which comes next, we do have ions. So basically we're breaking these compounds down into the ions that react. And that's a good idea because ions are actually the chemical species which are reacting in the reaction. So it's good to look at things at this level. Okay, so again, that's the ionic equation. Then we have something called the net ionic equation. And the difference between this equation and this equation is that some of the ions that were taking part in the ionic equation are not going to take part in the net ionic equation. So basically this should show, this one here should show sulfate being crossed off. Now why is sulfate being crossed off? Well, sulfate ions are known as spectator ions. So those are ions that don't actually take part in the chemical reaction. They're not actually reacting with other ions. Okay, so the net ionic equation would be the one you see here without the spectator ions. And that's the real difference between the ionic and the net ionic equation. Okay, so here's the net ionic equation. Now one thing that really helps to draw is a diagram like this one that you see here. So in blue you can see which ions are gaining electrons to become atoms here, and which atoms are losing electrons to become ions here. This is a really helpful way of drawing it. And so the blue text, because we have gaining electrons, that's reduction. The red text is oxidation, loss of electrons. Okay, now we're going to talk about oxidizing agents and reducing agents. So what are those? Well, a oxidizing agent is reduced and a reducing agent is oxidized. That sounds kind of different. Okay, so what is a reducing agent? A little bit more about that. It's a substance that causes another substance to be reduced. So since it's a reducing agent, it causes somebody else to be reduced. Okay, so that other substance is going to gain electrons, but these electrons must come from somewhere. Well, they come from the reducing agent itself. So as I said earlier, the reducing agent is actually oxidized. It loses electrons, and that's why it can enable another substance to gain electrons. Okay, so reducing agents end up being oxidized, oxidizing agents end up being reduced. So if you look at this diagram here, we see that zinc is a reducing agent. It donates electrons or causes somebody else to be reduced. And this here, Ra, kind of stands for reducing agent. So the reducing agent itself is oxidized, kind of all the opposite things for the oxidizing agent. Okay, now let's kind of think about something for a bit. That's why we've got this guy here. Why is it that when we look at this reaction here, why is it that these two guys react with one another, but these two don't? Well, it must be that Zn is a stronger reducing agent than Cu is. So Zn reduces Cu plus 2, but Zn is a stronger reducing agent than Cu is. So Cu is not able to reduce Zn plus 2 as well as Zn can reduce Cu plus 2. So Zn is a stronger reducing agent, and Cu plus 2 is a stronger oxidizing agent. And each one of these are stronger than these ones here. And that's why this reaction occurs spontaneously. In other words, it just happens. Whereas the other reaction on the right does not happen. Okay, so sometimes what we do when we're comparing the different strengths of various oxidizing agents and various reducing agents is to put them into a table. So I'm just showing two of them here in this table. A lot of times these tables are a lot larger. But what this one shows is on the left side of the table, the strongest oxidizing agents are on the left. So Cu plus 2 is a stronger oxidizing agent than Zn plus 2. The reducing agents, as far as they go, the stronger ones are below. So Zn is a stronger reducing agent than Cu. Okay, just a little question here. Again, be able to practice all these blue questions that are going to be on this recording here. So a reducing agent is an atom that, okay, what is it? It's oxidized, and so if it's oxidized, it's going to lose what? It's going to lose electrons. Okay, so chemicals only lose electrons, they don't lose or gain neutrons. So it's going to be answer C. Remember, a reducing agent is oxidized. All right, so here's an example of the kind of table we were talking about earlier. It's a little bit larger. This should all be one table. So if we're looking at this table, we want to know in this question which metal is able to reduce Cd plus 2. So that's this one right here, Cd plus 2. So we'll go on to the next page and talk about that a bit more. Okay, well when we look at the chart, we can see the strongest reducing agent is the ones at the bottom. So the way this works then is any reducing agent that's above Cd plus 2, so that's the other ones that are mentioned in this question, for instance, silver, copper, and gold, those are all above. So those are weaker reducing agents. So those are all above Cd plus 2. So they cannot reduce it. Whereas Mg is below Cd plus 2. So Mg is a stronger reducing agent. So we've answered the question. It says, which is the strongest reducing agent? Okay, now we're going to excuse me, kind of look at the opposite, an oxidizing agent. So it says refer to the table to determine which ion can oxidize Ni. So here's Ni. So remember, the stronger oxidizing agents are above. So any oxidizing agent that's above can oxidize it, and any below cannot. So since CO okay, so again, the weaker ones are on the bottom. So since CO, Fe, where's Fe? Right here, and Ca are below, they're weaker oxidizing agents. And on the other hand, since Hg plus 2 is above, it's a stronger oxidizing agent, as it says here. Higher you go, the stronger the oxidizing agent. Excuse me. All right, so there we go. So you just need to look on the table, and if it's not labeled this way, you need to remember that strongest oxidizing agents at the top, strongest reducing is at the bottom. Okay, question number 5. We've got a reaction going on here, and it says, what is the oxidizing agent? So let's see if we can figure that out. What we need to do is we need to look at the half reactions. So here we have Na on the left side going to Na plus 1. Well, if Na is going to Na plus 1, it's oxidation that's happening, right? We're losing electrons. We have 0 charge, we go to plus 1 charge. Oxidation is taking place. Now, since oxidation is taking place, since Na is oxidized, Na must be the reducing agent. Okay, so we know what the reducing agent is. It's Na. In the other reaction, we have, this is dichromate going to chromium plus 3. So, so we're gaining electrons. Okay, so since dichromate is reduced, it has to be the oxidizing agent. Okay, and this question actually said also, what is the oxidizing agent? And so that's going to be B. So we wanted to find both the oxidizing and the reducing. All right, so moving along. Which one of the following represents a redox reaction? Remember, to answer this question, a redox reaction always has to have both reduction and oxidation taking place. If it doesn't have both, it's not a redox reaction. Well, what we do then is we make half reactions for each one of these. So we have Na, which has a 0 charge going to Na plus 1. So we've got a loss of electrons. That's oxidation. We also have Cl2 going to Cl minus 1. We're going from 0 to a minus 1 charge. We're gaining electrons, becoming more negative. So that's reduction. So since we have oxidation and reduction, this is our oxidation-reduction reaction, or a redox reaction. So we already know the answer, but if we look at the rest of them here, so what I'm showing is each one of the half reactions, we have Ag is on the left side of the equation, we still have Ag plus 1 on the right. In other words, no change in charge. That's not oxidation or reduction. There's no charge here as well, there's no charge here. There is a change in charge with this one, going from negative to 0 charge, but we've only got 1 out of the oxidation reduction. We need to have both. So this is not a redox reaction. It's the same for C. If you look at each one of them, they're not gaining or losing any charge. And if we look at D, it's also the same thing. The charge is staying the same for each one of the ions on both sides of the equation. So it's not a redox reaction. Okay. So question number 7, which would be classified as oxidation? Now if we look at this here, when it says Cr2, that's the same as Cr plus 2. Okay? So when we go from Cr plus 2 to Cr plus 3, we're becoming more positive. We become more positive when we lose electrons, so that's oxidation. So you can see why that's oxidation. If you look at B, we're going from this to this. Now this should actually, I said both have 0 electrons. That's not true because this little dot here should be drawn larger. That should be H+. So we're going from positive to 0, but again, that's not oxidation. That's reduction. Okay, and here we're going from 0 to negative. That's gaining electrons. That's reduction. Going from positive to 0, again, that's reduction. So only A is oxidation. Okay, what we're going to talk about now is how we order metals by their increasing reactivity. I think we talked about in the last whiteboard session about how sodium burns brightly can even burn under water. It's a very reactive metal. And when we talk about reactive metals in this question, we're talking about metals that are good at oxidizing other metals. In other words, they can take electrons from them. So that's what we mean by reactive. So let's look at an example here and go from least reactive to most reactive. So we're going to analyze each one of these reactions one at a time. Well, if we look at reaction 1, we can see that B+ is able to take electrons from D. Okay? Because D is losing electrons. You can see it's becoming more positive. It's losing electrons, so B must be taking those electrons from D. And again, we said that when we're talking about reactive metals, we're talking about metals that can oxidize other metals. So B is more reactive than D, so we write that down. Then if we look at the third reaction, skip the second one for now, we can see that C is more reactive than B, because again, B is losing electrons, so C is able to oxidize B. Okay, so C is more reactive than B. So based on reactions 1 and 3, this is lowest reactivity going to B, and then B is lower than C. So the order is D, B, C. Okay? And if you look at reaction number 2, we skipped it because it was no reaction, but it actually confirms the same thing that's shown by reactions 1 and 3. So we don't really need to know 2, but it just kind of confirms the other 2. So if you just think about 2, you'll see why it confirms the other 2. All right. So moving on to the next one, it says, which metal from the last question is the strongest reducing agent? Okay, well, let's think about what a reducing agent is. It's able to reduce other substances by giving electrons to them, so it's oxidized in the process. Okay, so a reducing agent gives electrons. So if we look at reaction 1, D is the reducing agent. It's losing its electrons, right? So it must be giving them to someone else. So D is a reducing agent. If you look at reaction 3, you can see B is the reducing agent because it's becoming oxidized. It's giving its electrons to someone else. So it's a contest between B and D. And since we're not sure which one it is, we look at the reaction that has both B and D in them. And we can see that D reduces B. Okay, so D itself is oxidized. So D is the strong reducing agent. D is the strongest one because of reaction number 1. All right, so we got a little trophy here for D. There you go. All right, so let's move along. Now we're going to talk about predicting the spontaneity of redox reactions. So some of them happen spontaneously. They happen without adding any energy. So in this reaction here, the first ones happen spontaneously. The reactants do, but the products do not react with each other. So looking at the tables that we looked at earlier can help us decide which ones are going to react and which ones will not spontaneously. Now, there's some steps that we use to find out whether a reaction is spontaneous. First, we write the net ionic equation. Then we use excuse me, arrows to indicate a gain or loss of electrons. We identify the stronger reducing I'm sorry, reducing agent, the stronger oxidizing agent. Now here's the key part, steps 4 and 5. If the stronger reducing agent is losing electrons, in other words, it's being oxidized, and the stronger oxidizing agent is gaining electrons, in other words, it's being reduced, then the reaction will proceed spontaneously. In other words, if the reducing agent is doing its job, is doing what a reducing agent is supposed to do, and the oxidizing agent is doing what it's supposed to do, the reaction will proceed spontaneously. However, if the stronger reducing agent is not gaining electrons, if the reducing agent on the left side of the equation is not gaining electrons, and the oxidizing agent is not losing electrons, or rather, sorry, is losing electrons, the reaction will not proceed spontaneously. We'll see something that will kind of clarify that a little bit better. So let's look at one example of a reaction that's going to occur spontaneously and one that will not. Okay, so basically, in order for this reaction to occur spontaneously, we need the stronger reducing agent to be on the left side and the stronger oxidizing agent to also be on the left side, which they are. You can see a reducing agent is oxidized, and this is oxidized. It loses electrons, whereas this is reduced, it gains electrons. So this happens spontaneously. And again, the reason it occurs spontaneously is basically because the reducing agent, the stronger reducing agent, and the stronger oxidizing agent are on the left side of the equation. On the other hand, this reaction will not occur spontaneously. The stronger reducing agent and oxidizing agent are on the right side of the equation. So the oxidizing agent and reducing agent on this side are not doing the job that we want them to do. Okay, so again, in a spontaneous reaction, both the strong oxidizing agent and the strong reducing agent need to be found on the left side of the reaction. Good stuff. Okay, now we're going to talk about redox reactions involving ionic compounds. We know that a lot of times when we balance chemical equations, we can do them fairly easily by inspection. On the other hand, sometimes it takes more effort, and sometimes redox reactions can be balanced by using half reactions. So one half of the reaction is describing the oxidation that's occurring, and the other half is describing the compound being reduced. So let's look at this example here. Here's an overall ionic equation, and we're going to see that this part of it is the oxidation half. Why is it oxidation? It's losing electrons to become more positive. And we draw those electrons in here. And we can see that both sides of the equation are neutral. This has a 0 charge. This has +2, but it's also got 2 electrons, so it's 0 charge on the right as well. Now let's look at the reduction part of that same reaction. Okay, reduction, of course, is gaining electrons, so they're being added to what we have. Okay, so let's look at a question that kind of taps into this knowledge here. It says, in this reaction, what is the half reaction representing reduction? Okay, now you can't really see that well. You can't see it very well, but this should be Ag +1. Now sometimes they put a dot to represent that there's an ion, and there should be a very, very small dot here. But please know that this is Ag +1. Okay, so why is that the reduction reaction? Well, if we're going from positive to 0, we're becoming more negative, aren't we? And reduction is gaining electrons. We are gaining electrons here, right? This one's also gaining electrons, however, it's going from 0 to positive, which is oxidation. Okay, now sometimes when we balance half reactions, they may be in neutral solutions, sometimes in acidic, or sometimes basic. These 8 steps here are for balancing equations that are in acidic or basic solutions. I'm not going to read them here, but in a second we're going to be using these steps. So basically the first 4 steps are the same for acidic or basic, and then we carry on with step 5 if we have a basic solution. If we have an acidic one, we skip over to step number 8. Alright, so here's a reaction, a problem here. It says when you have this half reaction, when it's balanced in acidic solutions, how many electrons are gained by the oxidizing agent? Okay, so we need to do a few things here. We need to balance this reaction using the principles of acidic solution. We also need to find out what's the oxidizing agent. And once we find out what it is, we can find out how many electrons are gained. So let's look at these one step at a time. We're focusing on this reaction. And so first it says write the unbalanced half reactions. And this is the one we're focusing on here. Step 2 says balance any atoms other than oxygen and hydrogen first. So since we have Cr2, and here we have, we initially had just one Cr, we're going to add a 2 in front. So we're going to have 2 Crs on both sides of the equation. Okay, so we balance that. Step 3 says balance any oxygen atoms by adding water molecules. Okay, so we had 7 oxygens on the left, so we're going to add 7 water molecules because that's going to give us 7 oxygens. The next step says balance hydrogen atoms. So you can see we have 7 times H2, which is 14 on the right side. So we need to add 14 on the left side, and we do that by adding hydrogen ions. Okay. So now we skip to step 8 because we have an acidic solution, and it says now we want to balance the charges by adding electrons. So when we look at the charges that we have, we can see that we have plus 14 on the left and then minus 2. So 14 minus 2 gives us plus 12 on the left. On the right side we have plus 3, and that's times 2. So that's plus 6 on the right side. So plus 12 on the left, plus 6 on the right. We want to end up with the same amount. All we can deal with at this point is electrons, adding electrons, which are going to make things more negative. So if we add 6 electrons to the left, that's going to bring that plus 12 to plus 6. Okay, so on the left we have plus 14 minus 2, that gives us plus 12. And then 6 electrons gives us plus 6, and we have plus 6 on the right side. So everything's balanced at this point. And now the question said how many electrons are gained by the oxidizing agent. And so that is the compound that's going to be reduced. And we can see that the answer is 6 electrons. 6 electrons are gained. Okay, so let's look at redox reactions that involve molecular compounds. We've looked at ones that involve ionic, now we'll look at molecular. So for instance, if you're looking at cellular respiration, that's an example of a redox reaction. But how would you know it's a redox reaction? Because you don't have all those ions with positive and negative charges. The way you know that with molecular compounds is using a method called the oxidation number method. And we will look at that now. So we need to assign oxidation numbers. So the way we do that, well, let's look at our definition here. Oxidation numbers are the charge that an atom in a compound would have if no electrons were shared. So what happens is the oxidation number is given to the atom with the highest electronegativity. So for example, in water, O is more electronegative than H is. So when assigning an oxidation number, we think about it as if all the electrons belong to oxygen, all the valence electrons, and none of them to hydrogen. Okay, so let's think of that now. So with water, normally with water, it has oxygen has 6 valence electrons. It's in column 6. Hydrogen has 1 valence electron, but since O is more electronegative, we consider it that O has all the valence electrons. So it gets 1 from each of the hydrogen. So since there's 2 hydrogen, it's now going to get 8 valence electrons. So since it normally has 6, and now it has 2 extra electrons, oxygen is going to have a -2 charge. So that is the oxidation number it's given, -2. H, on the other hand, normally has 1 valence electron. Okay, so that's a -1. But since it's got 0 valence electrons, when we give all of them to oxygen, 1 minus 0 gives us a +1 charge. Okay, so that's how we get a +1 charge for hydrogen and a -2 for oxygen. Okay, so we're going to look at some oxidation number rules, and these can be found on page 456 of your textbook. So we'll go over these rules, and the first rule is that a pure element has an oxidation number of 0. So elements like sodium, bromine, all of them have an oxidation number of 0. Whereas if it's an ion, like Al+3, its oxidation number is just the same as the charge on the ion. So its oxidation number is 3. Now with hydrogen, in most compounds, they're going to be given, hydrogen is going to be given a +1 oxidation number. There are some exceptions, but most of the time we'll consider it to have a +1 charge. Same with oxygen. Normally it's going to have a -2 charge with some exceptions. All right, now in molecular compounds that don't have H or O, the more electronegative element gets a number equal to the negative charge it has when it forms ionic compounds instead of molecular compounds. So, for instance, when P forms compounds, or ionic compounds, it normally has a -1 charge. And S has a -2 charge. So that's the same charge it's going to have in molecular compounds. Okay, moving along. When you have a molecule like CF4, the sum of all the oxidation numbers put together in that molecule is going to be 0 because it's a neutral compound. So here's how we figure it out. Well, we know that F has -1, and so because there's 4 F's, that's going to be 4 times -1, or -4. That tells us that carbon must have a +4. Because +4 and -4 equals 0. So if we look at an ion, this overall charge is -1, so all these oxidation numbers have to equal -1 instead of 0. Okay, so we know that the oxygen atoms are normally given an oxidation number of -2, and there's 2 of them, so 2 times -2 is -4. So -4 plus this number has to equal -1. So that's how we know that N has to have an oxidation number of +3. That's how we can figure it out. Okay, I think what I'm going to do, guys, at this point is I'm going to stop it here. And when I start up the recording the next time, I'm going to start it off with doing some more sample problems with finding oxidation numbers, figuring out what they are. So we'll just wrap it up here. And so Go over these when you have a chance and make sure you can do all the problems we've done so far. Keep up the hard work, guys, and God bless and have a great day. Bye for now.